Hello everyone, we are Group 8 and this is our presentation about PageRank. This is our team. This is a table of our contents.
PageRank treats hyperlinks as votes in democratic system, but weight them risks based on source authority, meaning links from influential sites carry significantly more power. By incorporating a random submodel with a damping factor to ensure mathematical stability, the algorithm computes the principal eigenvectors of the Weber's matrix, thereby objectively quantifying the global importance of every page.
First, let's start off with a directed graph. Here we have a graph with nodes 0, 1, 2, 3, and 4, each having some number of arrows going in or out of them. And just like how we have learned during the semester, we can write down the adjacency matrix of this directed graph. This directed graph is kind of like if you were walking to different points in space. For example, if you were at point 4, the node 4, you could walk to node 0 or node 1. But what if we wanted to show that there is a different probability of you walking to different nodes? How would we do that? Well, we could write down the probability of you walking down each path next to the arrows on the graph. It is important to note that the probabilities of all the arrows going out of a single node have to have the sum total of 1, because having a probability more than 1 doesn't make sense. And so we can write down the probability matrix of this graph. This sort of graph is called a Markov chain. Also, it is important to note that in the probability matrix, the column represents where you are right now, and the row represents where you can go next. Before we continue, an eigenvector is a vector that is a non-zero vector, and it remains on its own span even after a matrix transformation, meaning the transformation acts like a scalar multiplication. So we can write that as a matrix multiplied by a vector is equal to lambda multiplied by the same vector, where lambda is just some number. Now, let Vt be the PageRank vector at time t. So Vt of I is the probability you are on node I at time t. So we define Vt plus 1 as the probability matrix P times Vt. Now, say we want to find some sort of stable state, maybe where this vector converges, where V is equal to P times V. And we rewrite this as P times V is equal to 1 times V, which is exactly the definition of an eigenvector with eigenvalue lambda equals 1. And this is where PageRank is actually kind of the same as linear algebra, because we can find the answer to this vector with linear algebra.
In this section, I will focus on logic behind PageRank, especially how it's computed using an iterative method called power iteration. Instead of solving the ranking directly, PageRank starts by assigning equal importance to all pages. Then, the algorithm repeatedly updates the scores through the matrix multiplication until the values become stable. The process models how importance flows through a network over time. Here is the workflow of the power iteration algorithm. First, we initialize all page scores equally. Next, we multiply the score vector by transition matrix, which represents how links distribute importance. After that, we normalize the result if necessary and check whether the scores have converged. If the values are not stable yet, we repeat this process. The algorithm continues looping until the ranking no longer changes. This slide, I'll explain how PageRank scores evolve over time. At the beginning, every page has the same importance. After each iteration, pages that receive links from important pages gain higher scores, while pages with fewer incoming links lose influence. As iteration continues, the distribution of the importance gradually stabilizes. This is why PageRank requires multiple iterations instead of just one calculation. To make process more concrete, let's look at a simple example with 4 pages. Based on the link structure shown here, we can construct transition matrix where each column represents how the page distributes its importance to other pages. We start with an initial score vector where all values are equal. Then we repeatedly multiply the vector by matrix to obtain new rankings. As shown in the iteration on this slide, the PageRank values change step by step and gradually approach a stable distribution. You may wonder why this algorithm eventually converges instead of changing forever. When the graph is strongly connected, importance does not disappear, but continuously circulates through the network. Repeat matrix multiplication causes the influence to settle into a stable pattern. As a result, the algorithm converts to a unique steady ranking that represents the long-term importance of each page. Another way to understand PageRank is through the random search model. Imagine a user randomly clicking links on the web page that are visited more frequently by this random server are considered more important. Power iteration simulates this behavior mathematically until the visiting probabilities become stable. This provides an intuitive explanation for why PageRank reflects long-term importance. To summarize this section, I focus on the logic of PageRank. I explain how power iteration updates scores step by step, how importance flows dynamically through links, and why the algorithm eventually converges. Finally, I use the random server model to provide an intuitive interpretation of the algorithm. This concludes my part on the logical design behind PageRank.
Next, we design the algorithm. Understand algorithm concepts through menu calculation. Please look at this miniature network diagram. We design 4 representative nodes. Node A, this is the most popular node. Everyone wants to connect to it. Nodes B and C, these are ordinary connects, responsible for passing weights. Node D, this is a developer design isolated node. Allow each pointer to others. No links point to it. Look at this matrix N on the slide. This matrix represents the link structure between 4 pages, A, B, C, and D. The value inside represents the weight of the votes. Our goal is through mathematical calculation. Observe whether the algorithm can automatically determine that A is the most important and D is the least important. Starting the iterative calculation. Iteration 0. We assume the network is equal, and each node is the initial vector V0 has a score of 0.25. Iteration 1. Perform the first matrix multiplication. You can see that since no one pointer to D, D's score is turning drop to 0, while A receives support from B and C, and its score rises to 0.375. Iteration 2. At this point, A's advantage is bent to 0.5. Because B, which pointer to A, receives support from A in the previous run, becoming a stronger node. So the score B gives back to A in the run is more significant. We continue the calculations and list the results in this table. Node D remains at 0. This is intuitive as no one recommends it. Node A, its score repeatedly increased and stabilized around 0.4, accounting for 40% of the network's importance. Although the numbers still fluctuate slightly, the rankings are lucky A approximate B greater than C greater than D. Finally, let's summarize the 3 core physical implications revealed by this manual calculation. Recursive authority. The rankings are not linear sum, but rather a result of mutual reinforcement. The strong get stronger, because a positive feedback loop is formed between authority nodes. Quality filtering. The matrix operations have a built-in filtering mechanism. We see that because D has a score of 0, the link from D to C is completely useless. This proves that the algorithm effectively receives noise. Low-quality links are invalid. Convergence and eigenvectors. Regardless of where we start, the system will eventually stabilize. This stable endpoint is in linear algebra, the principal eigenvectors of the matrix. This means that in a choice networks, there is an objective and unique order.
Okay, let's talk about the algorithm defects and corrections. In the algorithm, PageRank encounters 2 mathematical problems: dangling nodes and spider traps. First, dangling nodes, also called dead ends, occurs when a node has no outward connections. Second, spider traps occurs when a group of nodes are interconnected, forming a loop that doesn't lead to other nodes. I will explain the problem they cause and the corresponding solutions later with the diagrams and mathematical formulas. The first problem is dangling nodes. A dangling node is a node with only input but no output connections. Look at the diagram. Node B and node C point to node A, but node A point to node 1. So node A is a diagonal node. And with the diagram, we can get the matrix. So what's the problem with the matrix? The first column of the matrix is all zeros, and it will cause all PageRank values flow into A and disappear, which means after multiple iterations, the entire system will decrease and approach zero. And all of the PageRank value will become zero at the end. How do we solve the problem? We need to ensure every column sums to 1. By using this formula, H means the original matrix, E means a vector with all ones, and vector A is a flag to point out which column of the original matrix is all zero. As you can see, the first column of the matrix is all zeros, so the first number of vector A is 1, and others are zeros. And we multiply these two vectors with outer product and get the correction term. Due to that, every column needs to be summed to 1, so we divided the matrix by the number of nodes, which is 4. Finally, we add them together to get a corrected matrix S. And what we actually did is when we flow into the dead ends, we will jump to any nodes with the equal chains. The second problem is spider trap, which means one or multiple nodes are interconnected, but none are connected to external nodes. For the diagram, nodes A, B, and C are looping, and no one connected to node D. And we get the matrix from the graph. And if we use the matrix to iterate after iterations, the PageRank value of isolated nodes like node D will become 0. So the final PageRank value of D is 0. So what's the problem? All the points were taken by nodes A, B, and C. Even if node D were isolated, it should receive very few points and not 0. To solve the problem, we use a damping factor which is usually set to 0.85. For the formula, it means there is an 85% chance it will follow the original matrix, which is this one. And there is a 15% chance it will jump to any node from any times, which ensures that the score of node D will not converge to 0 due to being isolated. And we combine these two corrections. First, fill dead end, which is the S matrix. It only triggers when there is no path forward. And second, the random jump, which is the G matrix. It always has a 15% chance of triggering, whether there is a path forward or not. Let's go back to the diagram. We replace the original matrix with the corrected matrix and redo the iterations. As you can see the result, node D, which was initially assigned a weight of 0 due to being isolated node, now has a slight weight. This indicates that the algorithm has successfully simulated a more realistic and powerful network environment.
I will be presenting the real-world application and extension of PageRank. First, let's look at the academic world. Traditionally, we evaluate journals using the impactor factor, which simply counts the number of citations. However, PageRank introduced a more sophisticated metric called eigenfactor. By treating journal as a web page and citations as a hyperlink, we can measure quality, not just quantity. Basically, being cited by a top journal like Nature of Science is worth much more than being cited by an ordinary one. This algorithm helps us find the true authority in scientific literature. Next, we apply this logic to sports. A major challenge in PageRank is fairness. How do we compare two teams with the same win rate but different opponents? Using graphs theory, we treat each team as a node and every match result as an edge. When Team A defeats Team B, points or honor flow to Team A. The core logic is that points gained from defeats a strong team are weighted significantly higher than those from beating a weak team. This allows the system to objectively calculate the true strength of a team. Ecological applications. PageRank also extending to biologic. In an ecosystem, a food web can be viewed as a directed graph where energy flows from prey to predator. We use PageRank to identify keystone species. These are species that have higher linkage weight, even if their population is small. They play a central role in the network. Mathematically, we can predict that the extinction of this specific species could cause the entire ecosystem to collapse. This provides an early warning mechanism for the ecologists. Personalized PageRank PPR. Finally, let's talk about a modern extension, personalized PageRank PPR. The traditional PageRank assumes a random server jump to any page with an equal probability that damping fact. But in reality, users have specific interests. PPR improves this by changing the jump start. We create a dynamic bias vector that focuses on what the user likes. This modification is the cornerstone of the recommendation system you see on Netflix, YouTube, and social media today. Thank you.
And for the conclusion, the main core of our presentation, PageRank treats the link graph as a probability transition matrix. It is, for example, a Markov chain, and iterated Vt plus 1 equals to A times Vt, until it converts to the steady state V equals to AV, which the eigenvector for lambda equals to 1. And for validation, the 4-node hand calculation shows the score stabilize and capture the model in reinforcement of important nodes. And link quality weighting, like A is the highest and D is the lowest. And finally, the limitation and extension. Dangling node can lead to rank leakage and need correction. The same graph-based approach can be applied to citation analysis, score rankings, and ecological networks. Yes, and that's all of me. Thank you.